You have a large sheet in front of you with your group. Just hold on and listen for the instructions so that I don't have to give them to 28 different people, right? So you have a race car, a motorbike, and a fighter jet having a race. It's 2 miles long. It's on a runway. 2 miles long. So the questions are, who wins the race? Who has the fastest acceleration? Who loses the race? And I want you to draw the DT, VT, and AT graphs for the race and label the vehicle. So you should have 3 different sort of, you have like a position time graph, you have like a velocity time graph, and you have an acceleration time graph. And on each of those, you should have 3 lines or curves. One for the car, one for the bike, one for the plane. Okay? You have 10 minutes. Go. What is your question?
So they're all stopped and then they go?
They're all at the starting line, and they're all engines are running. No, they're all at 0. All at rest. Who wins the race?
Jet.
Jack?
I said the car.
How many people say jet? Who says car? Who says motorbike? Who has the fastest acceleration? Who says bike? Who says car? Who says jet? Who loses? Who says bike? Who says jet loses? Who says car loses? Okay, so the displacement time graph. I heard lots of people say it would be the same for each one. No, the displacement time graph also shows you the speed, right? And it's shown by the slope. Here's the learning part, guys. Listen. Josh, are you watching? Watch, learn. Okay? Would you agree they all accelerate? Okay, so they are all curved, right? So they are all curved. This is the first one, the displacement time graph. Now, which one has the greatest acceleration? The bike. So this one is the bike. Which one was got up to speed second? The car, and then the plane. But which one has a higher top end? The plane. So it, in fact, should get the steepest, right? And the bike should actually be, right? And the car had a faster one, so it's like this, right? And they all end up at the same point. It just takes them longer to get there, right? Okay. Now, velocity time. Let's make it a bit bigger. Velocity time. Now, velocity is how fast it's going. So which one gets up to speed the fastest? The bike. But then it reaches its top end and can't go any faster, right? So it increases in speed and then it reaches its top end and can't go any faster. Does this mean it's stopped? No, this is a graph of velocity. It's still maintaining a speed. So this is the bike. The car takes a little longer to get up to speed, but it ends up going fast. Oh, it ends up going faster, so it's going to go like this, right? And the plane takes even longer to get up to speed, but it has a much higher one before it maxes out, right? Something like that. Okay, now what about acceleration? The acceleration graph, and that's what we're going to look at today. The acceleration graph is a graph of the acceleration. Which one has the highest? The bike. Is it a constant speed? Sorry, a constant acceleration? Yes, until it can't go any faster, and then it actually goes to zero because it can't go any faster. This is the change in the velocity. The car doesn't accelerate as fast, but eventually it also reaches zero. The acceleration, the change in the velocity, and the plane accelerates for a much, much longer time before it even drops down to zero. It's the change in velocity. I'm guessing you didn't maybe get all of them.
Nope.
And that's fine. A nice little introductory activity. Okay. Let's talk about ticker tapes. Ticker tapes. And with those scenarios, we're going to draw some pictures. So the first one is easy. Constant positive velocity. If something has constant positive velocity. Now, you have all the text there as well. I find over the years it just works better if I explain it. But if you're going back to read it, then it sort of explains it all there. So I'm not going to bother reading it. If you want to go back and look tonight or over the weekend or come exam time, you certainly can. Constant positive velocity. Positive velocity means it's moving to the right in a constant speed. So what do the dots look like on your ticker tape? The same distance apart. So I would like you to take a moment, and in that space, you're going to draw graphs below it. So don't use up too much space. Draw dots the same distance apart, moving to the right. So you have to use a little arrow to show motion to the right. So you should have those dots drawn. Now, right underneath that, we're going to draw the displacement time graph. If it's moving at a constant velocity, what is the displacement or the position time graph, I should say? What does the position time graph show? What's the shape of it? Straight line? Right you are. It is a straight line that comes up out of the origin, right? How do we know it's constant velocity, Kaylee? Because the line is straight. Make sure you label it either as a displacement time or position time graph. Okay. Everybody with me? The next one is, that's up here too, Josh, right? Okay. The next one is the velocity time graph. Now here's something that I'm going to repeat probably 6 times today. The velocity time graph is a graph of the slope of the position time graph. So what is the slope? Is it positive or negative? It is positive, and is it constant or does it change, the slope? It's constant. So the slope is positive and it's constant, so my graph is going to be straight line or flat line? Flat line. Right you are. It is a flat line. You don't need to worry about the numbers on your picture. I just care about the shape and sort of where it is. So it's a flat line. Now, can you tell me approximately what value is the velocity here? Okay, 12, 11, something like that, right? What does that tell me about this graph? That is the what of this graph? It is the slope. It is the slope of this line, right? What does the corresponding acceleration time graph look like? It's going to be the same as this. The acceleration graph is a graph of the slope of the velocity time graph. So what's the slope of the velocity time graph? 0, says Connor. So what does that mean for my acceleration time graph? It's going to be flat, and it's going to be right at 0. We wouldn't want to draw stuff we didn't have to, right? Yeah, couldn't do that. What I do need you to be able to do at the end of it today is I should be able to sort of give you any scenario, and you can either draw the dots or draw the diagrams, or given one diagram, draw another one, or answer questions about it, that kind of thing. Okay? We're going to do lots of them, so don't worry if you're not getting it quite yet. I think the next one is constant negative velocity. Am I right? Okay, so constant, can I move on? Okay, I'll wait here. Constant negative velocity, what are the dots going to look like? Kaylee's still drawing, right? Okay. Constant negative velocity, what does the dots look like? Same thing, but the other way, says Lawson. And he's right. The dots are equally spaced. Nerdy professors would say equidistant. Equidistant, which means equal distance. The dots are moving to the left, show an arrow, draw an arrow, showing going to the left, and the dots are equally spaced. Constant negative velocity, which is to the left. You know how much practice it is, how much practicing I have to do at home to put my right hand up, point to the right, and say to the left? Last night I stood at home and I went left, right. How many people believe me? Thank you, Cam. Yeah, I didn't do it. Okay, what about the graphs? What do they look like? Position time graph. Moving to the left. What will be negative? The value? The slope? Well, okay, let's talk about shape. Is it going to be curvy or straight? How come straight? Going to the left, right? Equidistant, exactly. So it's going to be, but is it going to be straight and positive slope or straight and negative slope? Negative. Coming from the origin, down and to the left. Make sure you're doing it on the right one, right? The bottom one there on that first page. Constant negative velocity. Okay. The velocity time graph is a graph of the slope. What's the slope here? Positive or negative? Negative. Is it a constant negative? It's the same value, so it's going to be? Is that what you had in mind? Excellent. The slope of this line here is about minus 12. What do you think about acceleration? Same as the other one, says Connor. Really? How many people agree with Connor? You think it's going to be the same as the one above? Wow. I'm impressed. Why is it 0? Because the slope is 0. The acceleration time graph is a graph of the slope of the velocity time graph, and the slope here is clearly 0. So the acceleration time graph is 0. So if I asked you, can you tell what direction the object is going based on the acceleration time graph? You can't tell which way it's going, can you? You can't tell whether it's going right or left, up or down, really. Right? 0. Okay, you guys are doing awesome. The next one I think is positive velocity, positive acceleration. So the velocity is to the right, the acceleration is to the right. So this object is going to be speeding up to the right. So what are my dots going to look like? They're going to be more spaced out. Okay, so the dots are more spaced out. So what does my position time graph look like? Hey, yeah, Riley! What thing? What does the position time graph look like? Curved and going up? Like that? Curved and going up. Why curved? Speeding up, accelerating. Would you say the slope of the position time graph is changing? In fact, the slope is going from flat to steep, right? Which means because the velocity time graph is a graph of the slope of the position time graph, and the slope is, would you say, increasing? So what's the shape going to be? Straight and up or flat? Straight and up, right? Because the value of the slope, right? This is the value of the slope. The value of the slope is increasing. Give me the nod of understanding. Okay, so acceleration time graph is the graph of the slope of the velocity time graph. What's the slope? Is it positive or negative? Positive. Is it constant? It's constant because it's a straight line. So my acceleration time graph is going to be straight line? Flat line. Constant means flat, you guys. Flat and straight are two different things. This is a flat straight line. This one is a straight line, right? So does the slope change? No, the slope does not change. In fact, can you tell me what the slope of this line is, looking at this graph? What's the slope of this line, the velocity time graph, based on this one here? About 1.9, 1.8, something like that, right? About 1.8. The slope of the velocity time graph here is about 1.8, about this value. Okay, so we've done this one is positive velocity, positive acceleration, right? So what's next? Negative, positive, or negative, negative? Oh, positive, negative. Okay, so positive velocity, negative acceleration. Positive velocity means to the, negative acceleration means to the. So it's going to be slowing down. Which way? Positive velocity means it's moving to the right. So moving to the right and slowing down. Moving to the right and slowing down. Okay. This is going to the right. The positive velocity means it's going to the right. The negative acceleration means that it's changing and slowing down. In fact, at this point here, we should make a note, because if the signs are both positive, if the velocity and the acceleration are both positive, then it's speeding up. But if the sign is positive and negative, then it's slowing down. Is that going to be the same for negative velocity and negative acceleration, you think? We'll get to that. Okay. Thank you. Okay, so we got positive velocity, negative acceleration, so we're slowing down to the right, which means that my position time graph looks like this. Is that what you had in mind? Yeah. I kind of jumped, I sort of threw that out there before I could guess. Right? It's positive, and the slope is getting flatter and flatter. The slope is getting flatter and flatter. Right? The speed at the start is quite high, so the slope at the start is quite high. And it flattens out. Alrighty. Velocity time graph, what do you think? Okay, this is likely the hardest one. So this is how I describe it, or how I teach it. Would you say that the slope of the position time graph is getting flatter? Yeah. Okay, so that means that the slope is getting or approaching zero. The slope is approaching zero. Hang on, Alan, let me just finish this thought. The slope is approaching zero, which means the graph, which is a graph of the slope, has to go down and go towards zero. Like that. Is that what you had in mind?
I thought it was going to be like
Should it be like purple a little bit?
The velocity time graphs are going to be straight. It's approaching zero. Approaching zero, right? The graph of the slope, like you're looking for the slope here and here and here. You're taking a whole bunch of instantaneous slopes, and you're graphing them, so it goes down to zero. Well, if the object comes to a stop, then the velocity time graph gets to zero, yes. Good question. Adam, did you get your question answered? Yeah? Okay.
Yeah.
Okay. The acceleration one for this actually is not too bad. Let's talk it through. The acceleration is a graph of the slope of the velocity time graph. So is the slope constant here? It is. Is it positive or negative? It's negative. So we need a graph that shows a constant value in the negative region. So it's going to be Is that what you had in mind? All of these acceleration time graphs are flat. How come they're all flat? Because the acceleration has remained constant. If the acceleration is not constant, then you have that jerk factor, right? That kind of, right? Most objects will accelerate smoothly at a constant rate. How many we got left? 3? Okay, are we done this one? Yeah? Which one's next? Negative velocity, negative acceleration. Okay, let's talk this through. You had a little mental break there. Negative velocity, negative acceleration. Negative velocity means it's moving to the left. Negative acceleration means that's also to the left. So is it going to be speeding up or slowing down? Speeding up to the left. Easy. Speeding up to the left. Negative velocity, negative acceleration. Negative velocity means moving to the left. Negative acceleration is in the same direction. When the signs are the same, it's speeding up. When the signs are the same, it's speeding up. So we're speeding up to the left. So what does my position time graph look like? It's curving. This is slowing? No, this is speeding up. So that means it has to be getting steeper, but steeper negative. Like that? Like that? Steeper and negative. Okay, so velocity time graph. Describe the slope. It goes from flat to, Adam, up here, hang on, man. It goes from flat to steep, negative steep. So flat is that position or value of 0. So we're going from 0 to a negative steep value. Negative, there's the 0, and it goes away to a negative steep value. Okay, you guys are doing good. Acceleration is a graph of the slope of the velocity time graph. Here we have our slope is negative. Is it constant? It is constant, so it's negative and constant. And so it's going to be flat and below 0. And in fact, if I asked you to find the slope of this line, you would say it's about minus 1.8 or so. Okay, I'm running out of gas here. My velocity is slowing down. Yeah, I hear you. How many have I got left? 2? Okay. Negative velocity, positive acceleration. Negative velocity means moving to the left, but the acceleration is positive, like this. The signs are opposite, so it's going to be slowing down, but going to the left. Slowing down, but going left. Slowing down, but going left. Dots get closer together. Alrighty. So now, slowing down, but going left. So position time graph, slowing down, so that means the slope of the position time graph is going to be getting flatter, but it's going left, so it's negative. So how do we go left and get flat? Like that? Yeah? Negative and getting flatter and flatter because it's slowing down. The velocity time graph is a graph of the slope of the velocity of the position time graph. What's happening to the slope here? It's getting flatter, which means it's approaching 0. Are you guys listening? You're starting to lose focus here. Don't lose me. It's approaching 0, so the graph's going to go towards 0. And because it's going to go towards 0, and it's coming, I heard someone say it, it's going from negative because it's a high negative value here. So we're going to go from negative towards 0. Don't lose focus. Almost done. Velocity time graph. The acceleration time graph is a graph of the slope of the velocity time graph. Is the slope constant here?
Yes.
It is. Is it constant, positive or negative, Adam? Is the slope positive or negative here? Come on.
I don't answer now.
Up to the right. Positive. Is it constant? Is it straight? Yes. So constant positive. Flat and above. Relax, you guys. We should not go on a road trip. Only if our velocity is 0. Yeah. The acceleration is flat because it's maintaining an acceleration. It's accelerating, it's speeding up at a constant rate, and it's positive. Okay, last one. Put your pencils down. Do not draw this. Put your pencils down. Okay, so this one's called the passing lane. It's just sort of a bit of a summary here. I'm going to read this one, okay? I would suggest, if you want to draw it at the end, fine. Watch and listen, and then we'll be done right away, okay? So it says, observe the 2 cars below. The blue car starts ahead of the red car. Now, where do I have it? I have them like this, so let me just, okay, there we go. So I got a blue car and I got a red car, right? I think I can zoom in a smidge. Okay, which one is going faster? How can you tell the red one? It goes past it, right? Would you say the blue one starts ahead of the red car? Where does the blue car start? The blue car starts at 20, right? The red car starts like negative something, right? But the red one's definitely going faster. So what will the position time graphs look like for this? Will they be curved or will they be straight?
One will be curved.
Well, I will tell you this, it's kind of hard to see it, but both of them are moving at constant velocity. Neither one is accelerating. So both of the position time graphs will be straight. Which one will be steeper? Red. You can draw it now if you want. But you can't, like, you don't have the car there, right? So if you want to draw it, you go ahead. I don't think it's going to be much use to you. Yeah, it's all about the animation here. That's right. Would you agree that the red car catches the blue car? Yes. Josh, at what time does the red car catch the blue car? Josh, at what time does the red car catch the blue car? Can you tell? No, at what time? No, at what time? 7 seconds, right? Would you agree that's when the positions are the same? Okay. 7.0, yeah. Oh, yeah, maybe. Okay. Well, I thought maybe you were reading it off here. Fair enough. 7.0. Please keep that in mind for grade 12. The 2 cars catch each other, or the red car catches the blue car when the positions are the same. That's first unit, grade 12. Okay, what do you think the velocity time graphs are going to look like here? Draw what you think they're going to be. Draw what you think they're going to be. What do you think the velocity time graphs are going to look like? Go ahead, try it. They're both moving. They're not accelerating. They're moving at a constant speed. They're moving at a constant speed and they're going to the right. Go ahead and just draw it. I'll show you the answer right away. It's okay if you get it wrong. Okay, so what do they look like? 2 flat lines. On top of one another, or how are they arranged? The red one is higher. Adam, we're almost done. Hang with me here, man. Why is the red one higher? Going faster. Why does the red one not start until here? It doesn't appear until 4 seconds has elapsed, right? Okay, one last question and then we're done for the day. Just hang on, 30 more seconds. Can you tell from this graph where they cross?
No.
Can you tell from this graph where they cross? Well, we know they cross at what time? 7 seconds. So, like, can you tell from here? You can't tell yet. I will show you next week how to tell. Thanks. You guys did awesome today.